Welcome back to the Math Professors. We cover topics that can be found in any college math class. I'm Professor Van Hamlin. I'm going to cover logarithmic functions today. So if you like the content, please consider liking, subscribing, and sharing. So the logarithmic function of base b is defined by f of x is equal to the log base b of x. Now if you want to know how to write this, let's kind of take this back to like grade school. What the logarithm does is it's log, and this base is a subscript. So that's how you would write the log base b of x. All right, now the log base b of x is defined by really this equivalency, that if y is equal to log base b of x, this is equivalent to b to the y is equal to x. So we are used to some common equivalencies, something like 6 divided by 2 is equal to 3, which really means that 6 is equal to 3 times 2. You know, all I did is just take the 2 and multiply it to the other side. Similar here. 7 plus 1 is equal to 8, well then 7 is equal to 8 minus 1. I just subtracted 1 to both sides. If the square root of 9 is equal to 3, well the way we get rid of the square root is we square both sides. So the square of this side would be equal to the square of this side, so 9 is equal to 3 squared. And then similarly, the sine of pi over 6 is equal to a half, which means that pi over 6 is equal to the sine inverse of a half. So we're used to, going back and forth. I really want to go back and forth with a logarithm that's not nearly as familiar. So let's practice that so it seems just as familiar as these. So what I want to do is I want to convert the exponential form equation to its equivalent logarithmic equation. Now, what you'll learn is that the logarithm is really the exponent. I was told to say that over and over and over again. Like, what is a logarithm? Well, a logarithm is an exponent. So what we can see over here is this equation says the log base b of x is equal to y. Now when I write this as an exponential equation, you notice that y is the exponent of this exponential equation. So when I say the logarithm is the exponent, that's really what I mean, is that if I isolate this for the exponent, you get the logarithm. So what I want to do is I need to isolate this thing. So when I have something of this form. This is b to the y is equal to x. So what I know is that y is the exponent. So when I isolate that exponent of 2, what I'm going to get is I'm going to get the log base b of x. Now the base of this exponential equation is equal to 3, and this is 9. So what we can see when we see the logarithm, this says that 3 squared is equal to 9. Now the way I kind of remember this is I know the logarithm is immediately equal to the exponents, and then the base is obvious. And since there's only 3 things here, the argument of the logarithm, which goes, x is the argument of the logarithm, is going to really be the thing that's left over. Let's rewrite this as an exponential equation, just in case we forget that the square root is the 1/2 power. Okay, so if I were to write this as a logarithm, I'm really just isolating that power. Now the logarithm is equal to the power. So the power, is equal to the log of something. Now, what's the base of this exponential equation? Well, the base is, 16. So that means 4 is going to have to be our argument. And we can see 16 to the 1/2 is equal to 4. And then similarly, when I isolate that exponent, because remember that the exponent is equal to the logarithm. Now the log, what's the base? Well, the base of the exponential equation is 9, and then this is going to be 27. Now what I want to do is let's do this in reverse. So we'll erase this and set up another one. So what I want to do is I want to convert the logarithmic form equation into its equivalent exponential equation. Something I forgot to mention is when we're talking about logarithmic equation of base b, we are verifying that b is bigger than 0. So I really should put this up here that, b is always going to be greater than 0. For the same reason when we're doing an exponential equation, we do the same thing because we're trying to make sure that we get real value outputs, and we don't want to have complex numbers in here. Okay, so let's rewrite this as its equivalent exponential equation. So the first thing I like to start out with in this case is I like to go after the base first. So the base of the logarithm, this says log base 4 of 64 is equal to 3, so the base of the logarithm is going to be equal to 4. Now remember, the logarithm is always equal to the exponent, so the logarithm is equal to the exponent, which is 3. So this is finally going to be equal to the only thing left over, which is going to be 64. You can check that. 4 cubed is 64. Similar here. What's the base? Well, the base is going to be 64. It's the log base 64. The logarithm is equal to the power, so 1/2, or the square root of 64, is equal to, that 8. And then similar here, this is the base, so 1/4 raised to the negative 1/2 power is going to be equal to 2. And we can even check this. This is kind of an interesting one. So this is well, this would be 4 to the 1/2 power, which would be equal to 2, which checks out. All right, so let's evaluate some of these things. I want to be able to see if I can determine what the logarithm is equal to. So what I want to do is evaluate the logarithms, and remember what we know about logarithms is that if I have y is equal to the log base b of x, this is equivalent to b to the y is equal to x. So really what I'm going to do is I'm going to use their equivalent exponential form to be able to solve these things, and just because we tend to be more familiar with the exponential versions of things. So the first thing I'm going to do in order to evaluate this is I'm going to say let y equal the log base 2 of 8. Now when I do that, I'm going to rewrite this as an exponential form. So the base is 2, the exponent is what the logarithm is equal to, and this will be equal to 8. Now once I have this of this form, I know I can write both of these as a power of 2. So 2 to the y and 8 is 2 cubed, and since they are both base 2, that means their exponents have to be the same, so therefore y is equal to 3. So that's what this is. Remember I said that the log base 2 of 8 is equal to y, so you know this thing is 3. Now we can verify that. So 2 cubed is equal to 8. All right, let's do the same thing here. So what I'm going to do is I'm going to write this as y is equal to the log base 9 of 3, and then I'm going to rewrite it in its exponential form. So this has a base of 9, an exponent of what the logarithm is equal to, and this will be set equal to 3. Now I have to write both of these as their common base. Well, 9 is base 3, and so is 3 is base 3. So what I can do is I can write 9 as 3 squared is equal to 3. Now we know when we raise powers to powers, we multiply the exponent. So this is 3 to the 2y is equal to 3 to the, well, since there's no power, it has to be a 1 there. So that means since the bases are the same, their exponents have to be the same. So y is equal to a half. So this is equal to 1/2. And we know that 9 to the 1/2 is equal to 3 because the square root of 9 is 3. All right, one last one. So very similar, I'm going to set this equal to y. Y is equal to the log base 16 of 64. So to rewrite it as its equivalent exponential, base 16, exponent y, because that's what the log is equal to. So the exponential will be equal to the argument, so 64. So what's the common base now? We have some choices. We could use 2, we could use 4. Let's use 4. So 16 is 4 squared to the y, and 64 is 4 cubed. Now if I decided to do 2, this would be 2 to the 4th, and this would be 2 to the 6th. But it'll still give you the exact same number. So we really technically should use the smallest base, but I just chose one that'll be, we already did 2 over here. Okay, so now we have 4 to the 2y is equal to 4 cubed. Since the bases are the same, their exponents have to be the same. So 2y is equal to 3, so y is equal to 3/2. So that means this logarithm is equal to 3/2. So here's some properties of logarithms. What we know is that the log base b of 1 is equal to 0, and we can verify this by using the equivalent exponential. So in this case, the base is 0, the base is b, the exponent is 0, and this is equal to 1. And we know that anything to the 0 power is 1. So that one checks out. For this one, let's rewrite it as an exponential. This says b to the 1 is equal to this b, and again, that checks out. Very similar here, I can prove these inverse properties, and really let's talk about what they mean. This says the log base b of b to the x is just equal to x. What this is saying is that the log base b is the inverse of the exponential base b. That what we have is we have something of the form f of f inverse of x is equal to x. Now this is where we're saying that, you know, f of x is our log base b of x, and then f inverse of x its inverse is going to be equal to b to the x. So they're inverses of each other. I could switch these things and switch these, because for a function to be an inverse, it also has to work the other way. So f inverse of f of x also has to be x, and that'll still work. That's actually what this one is. So we can also verify that this is true by just rewriting it as its equivalent exponential. So, this is the base down here, this little b, and its exponent is what the logarithm is equal to, and this will finally be equal to the argument, which is this b to the x. So that's true. And then similarly here, this says in order to actually do this, I'd have to log base b both sides. So this would be the log base b of this side of x is going to be equal to the log base b of this side. So if I log base b this side, this b will go away, and if I log base b this side, it's going to be log base b of x. So we're going to use these inverse properties to evaluate some logarithmic equations just a little quicker. So let's erase this idea. Let's just do just a couple quick examples to show that. So what if I want to evaluate the logarithm? We already know that we can turn it into its equivalent exponential equation, but I want to do this using using inverse properties, which tends to be a little quicker when you see it. As long as it's not a super complicated one, it tends to be pretty quick. So if I say let's kind of go back to the trust story. What about the log base 2 of 8, for instance? Well, I can evaluate this thing because I know I can write 8 as 2 to a power. As long as I have the log base b of b to a power, the log base b is going to annihilate this exponential base b, so we're just going to get its exponent back. So what I mean by this is this 8 right here, I can rewrite that as 2 cubed. So this is going to be the log base 2 of 2 cubed. Now the log base 2 and the exponential base 2 are going to cancel, so what we're going to get is we're just going to be left with that 3. Now as they get more complicated, it's harder to see, but remember, for me to be able to simplify this logarithm, I have to write 9 as a base 81. And I can do that. I can, I know that 9 is actually the square root of 81, or 9 is equal to 81 to the 1/2 power. So what I can write is this is 81 to the 1/2 power, because that's what 9 is. As long as the bases match up, they will annihilate because they're inverses, so this will just be equal to its exponent of 1/2. So we in. That's enough. Okay, that's enough.